Birth month may not be related to success as a CEO, but what about on the ball field? It's been proposed by some researchers that children who are the older ones in their class at school naturally perform better in sports, and that these children then get more coaching and encouragement. Could that make a difference in who makes it to the professional level in sports? Oftentimes, parents have to think about, should I hold my child back so they're older in their class so they do better at school and in sports? Baseball is a remarkable sport, in part because so much data are available. We have the birth dates of every one of the 16,000 players who ever played in a major league game. Since the effect we're suspecting may be due to relatively recent policies, and to keep the sample size moderate, we'll consider the birth months of the 1478 major league players born since 1975 and who have played through 2006. We can also look up the national demographic statistics to find what percentage of people were born in each month. Let's test whether the observed distribution of players' birth months show just random fluctuations or whether it represents a real deviation from the national pattern. If we look at our data, we can see that we have each birth month with the requisite number of births for major league players in our given time frame. Additionally, I've pulled up the data from the national percentage for births, and what we want to do is calculate the expected births for each month. So I'm going to call that in our calculator EXP births. And I'm going to hit enter. And the way we calculate expected births will be our total number times our national underscore percent. And if I call that column with each of the percentages, it should give me my expected birth values. There are 1478 players in the set of data. I'd expect 8% of them to have been born in January, so 1478 times 0.08. I won't round off because expected counts needn't be integers. Multiplying 1478 by each of the birth percentages gives us the expected counts shown in the table. Before we jump to the calculator, we have to make sure we check the assumptions and conditions to make sure that they are met for a goodness of fit test. So, our counted data condition. We have month-by-month counts of baseball player births. The independent assumption is these births were independent. Our randomization condition is, although this is not a random sample, we can take these players to be representative of players past and future. All of our cells that we've calculated are greater than 5. And then our 10% condition is these 1478 players are less than 10% of the population of 16,804 players who have ever played or will play Major League Baseball. So it's okay to use these data for a goodness of fit test. So just like before, we want to look at a histogram to see what the distribution looks like. So I'm going to hit Control, Doc, and I'm going to add data and statistics. And again, I'm going to select the birth month, which gives me my start of my bar chart. And then I'm going to go to Menu and then Plot Properties, and I'm going to add a Y summary. And this one, we want the birth count for each month, which gives us our distribution. And we can kind of see that those summer months, there's a little lag in July, which is usually the cutoff for year for playing a sport. And then you see a large jump in August and September. And that's what we want to focus on is, are these counts due to random sampling or is there something fishy going on? So what we need to calculate, just like we did before, is we're first going to calculate the residual. So I'm going to call it RISID, and that is going to be our birth count minus our expected birth. And this will give us the residuals for each of those cells. And then what I want to do is calculate the residual squared. So I'm going to call it RISID-SQ for squared. And that's just going to be RISID raised to the second power. So this is our squared residual. And now what we want to do is sum all of those up to calculate our chi-squared. So to calculate chi-squared, we're going to take our residual squared, and we're going to divide that by our expected birth. So this gives us the contribution for each one of those variables. And what I want to do is sum those up. So I'm going to say G1 colon G12, which gives me all the contributions. And I get a chi-squared statistic of 26.48, which seems relatively high. But let's compare this to our distribution. So what we want to do is hit Menu, Statistics, and we want to go to Distributions here. We're looking at a chi-squared CDF because we want to sum up everything. And this will be 26.92. Our upper bound, let's just say, is 999. Our degrees of freedom is how many months there are minus 1. So that's 11. And I want to draw and shade the area. So you can see, okay, my test statistic was a little off. So this will be slightly different. But we can see that this probability, we can barely even see any shaded region for our cut point, which is really small, which is 0.004. So there is something going on with this test statistic. So let's just try it in a different fashion so we can see what's going on here. So again, I'm going to hit Control, Doc, and I'm going to add a calculator. And here we want to do a goodness of fit test. So I'm going to hit Menu, and I'm going to go to Statistics and Tests, and we're going to go chi-squared GOF for goodness of fit. I want to look at the birth count versus my expected birth, and our degrees of freedom is 11 because that's how many categories we have minus 1. And here I get my chi-squared statistic of 26.48 and my p-value of 0.004. If we're comparing this to a significance level of 0.05, our p-value is sufficiently low, which would lead us to reject the null. Additionally, if we want to see which one of these months is having the most significance on our chi-squared statistic, we can go to var, which are variables, and what we want to do is look at our stat compilation list. And we can see that for January it's 2.97, February 2.97, then 0.04, so these are relatively small for March, April, and May, and into June, July, and then there's our big value of 7.23 and then 7.68 for September, and then October, November, and December are all relatively small values. And these are the exact same contributions to our summary statistic as what we found with our chi-squared test for each of the cells. And we can see from our data that these months right here are having the most impact on our chi-squared statistic. So going back to our null hypothesis, our null was the distribution of birth months for Major League Baseball players is the same as the general population, and our alternative is the distribution of birth months for Major League players differs from the rest of the population. So we calculated our degrees of freedom, which is 12 minus 1. We got our chi-squared statistic, which was 26.48, as we saw from the spreadsheet. And we found our p-value to be 0.0055, also from the calculator. And because the small p-value, all we can do is reject the null hypothesis and conclude there's evidence that birth months of Major League Baseball players have a different distribution from the rest of us. So I hope this example was helpful, and we're going to do a couple more to finish up the goodness of fit tests.